Lesson 9 is on thermochemistry, which is the relationship between energy and substances. One difference between taking 1409 and just 1411 is that you actually get more thermodynamics in 1409 for engineers. Some of the thermodynamics that we cover is normally in 1412. Anyway, so that's one reason for this class, is that it allows you to get more thermochemistry in your one semester class. So we have 2 lessons of thermodynamics basically. Anyway, so it's important in chemistry because of energy, like fuels and all of that, but we're also going to look at like phase changes and heat flow and how that affects things as well. So some basics on that. I think every engineer has like a 2000 level general thermodynamics class, and this will get you going on those. But anyway, so a definition of energy is that it's basically the capacity to do work or to move matter. Energy is converted between types but not lost or gained. You know, without a nuclear reaction, it's not lost or gained. And the energy for the universe is constant. And, you know, we say the energy for the universe, that means that, you know, if you consider the whole universe, that's fine. But actually, we more often will say for a closed system. In other words, if you have what we call a closed system, energy can be converted from one type to another, but is not lost. And let's look in a second at what a closed system is. We're going to first consider a simple system, and we're going to do this one in lab. So where we're basically going to put a hot object in water. We will put hot metal in water. So heat is the transfer of thermal energy due to a temperature difference. Of course, heat always travels from hot to cold. So we don't usually say, you know, heat is the movement. We don't say that something has a lot of heat. We would say something has a lot of thermal energy. If it has a high temperature, its particles are moving fast. We refer to the heat as the flow. So we use the symbol Q. And here's what I'm talking about for as far as a system goes. You can draw a system, you know, just for theoretical terms or problem-solving terms wherever you want. And in this case, the imaginary division that I'm drawing is this dotted line, and that's kind of you know, just to problem solve and to organize things. I might kind of imagine, okay, the hot object is my system, and the surroundings would be everything around that. So the surroundings in this would be the water, mostly the water. So this is called an open system. And it's called open because energy is crossing the boundary. Okay, so in this case, the hot object is going to be losing energy, or in the form of heat, to its surroundings, and its surroundings will warm up. So that's an open system. The law of conservation in energy involves a closed system. So if I imagine the boundary larger, now it's closed because no energy is being transferred here. And that's the assumption I'm making. I'm assuming that this insulation is not allowing for heat flow to occur out here. So if this is true, so this is a closed system. And if this is true, that means that all of the energy that the hot object is losing is being gained by the water. Okay, and so the Q for the hot object is the opposite sign as the Q for the water. So what I need to tell you, and I was just looking to see where, is that Q, it is going to, when you look up a Q, it'll be a number in joules or kilojoules, but it also has a sign. It is positive for something gaining heat. and negative for something losing heat. So in this case, the hot object, I'm going to say, just point to it, that hot object would have a negative Q. It would have a negative number for its Q, and the water would have a positive Q. And so they would be the same number, opposite signs. Specific heat gives us the relationship between the amount of energy absorbed and the temperature change of that substance. And this is a physical property that varies from substance to substance. For example, a metal with a small amount of heat will warm up more than a piece of plastic, will warm up less, or water is known for requiring a lot of energy to warm up. So this is again, a physical property. Specific heat, and it is normally, or we'll see it mostly in joules per gram degree C, the amount of energy to warm up 1 gram of a substance 1 degree Celsius. And this equation we'll be using a lot. This equation is written differently in different fields in chemistry versus physics versus engineering, but the general idea is the same, that especially this part is written differently. But anyway, so Q again is our heat, and it will be in joules. And S is our specific heat. We said that. M here is mass. And delta T, I told you, and the mass will be in grams. Delta T will be in degrees C. This one, again, this is kind of another form. This right here takes into account the object and its specific heat. So if you're talking about a specific object, like you have a specific, I don't know, pellet of metal or something like that that has a set size, you may have its heat capacity, and instead of putting together specific heat and mass, it's kind of all built into that one thing. But anyway, that's what I mean by it can look different. So we can do some problems using this, because we can compare the heat and temperature change of one thing, like our hot piece of metal, to another thing like the water.